Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
What I want to do is introduce Jim Laris. Jim is an old friend and colleague of mine in the Extreme Computing Group at Microsoft Research. He's got an amazing background in programming tools and system architecture. He's studied parallelism and concurrency, software engineering, just about everything in the business, and accomplished quite a bit. And he's been working in our group on looking at the cloud now for about 3 years. And I'm sure you will enjoy his presentation. He will talk about how the cloud will change everything. Jim.
Thank you, Dennis. If you can't hear me, tell me, because I'm told that I can't hear the speakers. Thank you, Kent and Dennis, for the invitation. I'm very pleased to have this opportunity to talk about some speculation about the future, and a little bit about what the Extreme Computing Group is about, which is what Dennis and I are both part of inside Microsoft Research. So let me just set out a roadmap for this presentation. I'm going to talk about the technology trends that are shaping the world now, and really sort of ask the question, what comes after the PC? I mean, I think all of you have pretty much an idea that what's coming is going to involve the cloud. What I'm going to argue is that people see the pieces, but they're missing the big picture for it, seeing the individual trees in the forest. The big picture I'm going to argue for is that the combination of devices, many devices, not just cell phones and iPads, but PCs, cell phones, iPads, embedded devices, special purpose devices, plus the cloud is a computing platform, and it is the computing platform that all of us are going to be doing some incredible stuff in the next couple decades for. I'm going to talk a little bit about the things that we hope that this new computing platform are going to enable, the changes of experience, basically making the computers a lot more helpful to people, and then talk about what XCG is using to drive this innovation. So, this is a great slide. This basically sort of reminds people in this room, and I think most of you are old enough to remember this. Sometimes when I give this slide, I realize that most of the audience doesn't remember this. But, it wasn't very long ago that all the stuff that we take for granted really just wasn't there. For instance, I have a bunch of teenage, slightly older kids who can't imagine that you could possibly have gone to school without word processing and Google. They're just like, how did you do this? And I'm just like, huh? But, it wasn't very long ago, and the rate of technology progress is just pretty phenomenal. And one of the dangers is that I'm now giving a talk and talking about the future, and it's very hard to predict, particularly about the future. And so just to keep myself honest, I found a bunch of these great quotes where people have gone and predicted the future and have been absolutely embarrassingly wrong. So if you want to read a few of them, you can basically sort of see how wrong very smart, very well-informed people can be. I'm going to undertake that in this talk with full knowledge of this, but basically what you should take away from this talk is a real deep look at the trends that are going on and some speculation about what those trends are going to lead us to. So, one thing to look at is the sort of rate of progress, this exponential progress. And I think many people have the feeling that things are getting faster. Things are sort of growing more and more complicated. Certainly, most people who are out there who are not computer scientists, people who are in our field, see technology as changing really rapidly, changing underneath them. They may like parts of it, but in some sense it's baffling. For a long time, computers were something that someone else used, and you saw the effect of computers. Then all of a sudden, computers were at the office. Then computers were in your house. And then computers just became an integral part of your life that you couldn't really imagine living without. And I think that's the point we're at today, is where computers are really sort of a consumer item. Now they've started to diversify, and they're available in small form factors, mobile form factors. But for many people, it's still an opaque black box. You still have to sort of deal with the idiosyncratic nature of computers and the fact that they don't really seem to interact all that well with humans. And this is a real challenge. I think this is, in some sense, one of the major challenges that our field faces in the next few decades, is how to make computers and people work together better. And one of the arguments I'm going to make in this talk is that the combination of the cloud plus a large number of devices is a very, very powerful platform for addressing this concern. So what's changing? Let's try to sort of step back and look at the sort of changes as separate trends, not sort of see where they're going quite yet. So one thing is that we are now able to put a tremendous number of transistors on a chip, and we're now able to integrate systems on a chip. Key thing there is that that just drives down both the cost of computing plus the cost of communication. And this is a key thing, is that now you can put a radio, a wireless radio, on a very inexpensive device, and so that device now is part of the network, and that device can communicate with other devices, and it can communicate with the cloud. This is a key thing. I mean, I remember when this really was driven home to me with the Kindle, where you sort of bought the Kindle, and you didn't even realize it, but it had a cellular modem in it, and you didn't have to activate it. It was just there. It was just part of the device, and this was something that's originally sold for a few $100s, and it's even less now. So this can be embedded in everything. So now we have computing and computation that's incredibly cheap because of this high level of integration. We also have very, very powerful processing units, the graphic processing units, which allow us to do a lot more realistic graphics and ubiquitous realistic graphics. And we're starting to see the integration of the CPU and the GPU. So no longer do you have to go out and buy an expensive card. It's now available on all of the CPUs, and it'll become increasingly true. We're also seeing a tremendous growth in data, and I probably don't have to tell this audience there, but I have some interesting slides later sort of really documenting how fast data is growing and how much of an opportunity and challenge this is. I mentioned embedded computing, but now we're starting to get to the point where you can literally embed computing in a large number of objects. You can build wireless networks, and basically things can talk to each other and talk to you. And obviously, you know, as I said, wireless, there's a huge amount of pressure on the spectrum. You know, there's a lot of devices out there that are going to want to communicate, and we don't have all that much bandwidth currently for them. And of course, you know, software is changing. You know, if you look at the latest trend in terms of the web and the networks that are, the websites that are available there, it's quite different, and it's quite different in a very short period of time. You know, who would have predicted 5 years ago that social networking would have been sort of the central thing in terms of computing? That people were basically going to go flock to this website, Facebook, or that, you know, we're going to start having, you know, a .com boom all over again in social networking sites. And this is a really interesting trend because it basically says that there's room for a huge amount of innovation in terms of computers and computing. Okay, so, you know, this is basically just another view of it. Let's dive in and start taking a look at it. It's always good to sort of ask why we're an exponential field. And the answer is that underlying all of the change that's going on in our field is Moore's law still. You know, this is basically the original observation by Gordon Moore that the number of transistors that you could fabricate in a unit area of silicon was doubling every 18 months or 2 years. This is still true. You've all seen graphs like this one, which basically say performance is leveling off. And people always conflated performance and the number of transistors because the two were intimately connected for many years. Around 2004, 2005, we reached a watermark where we basically said we can't clock the chips any faster, which used to be a characteristic of Moore's law. But we can keep on increasing the number of transistors. And so you're seeing doubling in the number of cores. And you know, that gives us potentially more computing power for applications that can use it. And the web is certainly, and the cloud is certainly one area in which can use this very effectively. As Moore's law sort of peters out, and you know, there's a debate as to whether we're going to get 2 or 3 more generations of scaling, but you know, the real message there is that we only have a few more scalings of semiconductors until we're reaching these atomic limits where literally, you know, you count the number of atoms in a gate in small single digits, and we'll no longer be able to scale it down. As that happens, what's going to happen is we're going to ask a question, a very profound question, which is, what's the best use of a transistor on a chip? You know, right now, a lot of work has gone over the last 30 years to basically using that transistor to build more effective general purpose processors. That's not the only thing you can do with it. You can build special purpose silicon devices that solve one problem and solve it particularly well. And this graph is really interesting. This graph is basically a plot of the energy efficiency. Think of it in number of ops per nanojoule that you can do of, I think it's about 20 papers that were published at ISCC, the Circuits Conference, over a period of a few years. And basically what this shows is that there is a huge difference in the energy efficiency of general purpose processors, DSPs, which are processors that have been specialized to a particular domain, and then dedicated hardware. And huge means literally 4 orders of magnitude difference there. And so what this says is that if you really, really are interested in energy efficiency, then you should be thinking about using that transistor for something besides a general purpose processor. And I think you're going to see lots and lots of innovation in this space in the next couple of years as people realize that there's no good reason to build yet another core on the chip when they could go and use the area and the transistors to build specialized devices. And this is actually a very, very positive trend because it means that the performance gains that we're getting from silicon are going to continue. They're just going to continue in more heterogeneous forms than we've seen. The other thing that is really sort of striking about the cloud plus client computing is that power has become a first-rate consideration at both endpoints of the spectrum. So if you look at data centers, power just sort of literally dominates your consideration in terms of how big you can build your data centers, how you program the data centers, how you build the equipment within the data centers. And obviously at the other extreme, in terms of small battery-powered handheld devices, power dominates there. You know, literally if you can't get a full day's use out of the batteries in your device, you're in serious trouble. You know, people don't find your device attractive. And so that really sets parameters in terms of what you can do, what you can put in the device, how the software operates. So power matters. The other thing is that as we sort of push the internet out to the Internet of Things, power is going to matter even more. As we start building computation and communication into embedded objects and devices, power becomes an even bigger consideration because we can't afford to put large batteries into very small devices. And we can't afford to connect them all to power lines either. So, you know, what does this mean in terms of computing? Well, if you look at the picture today, basically, you know, almost every computing device looks like this. You have a CPU, you have some stuff around it, and maybe you have a GPU to do graphics. In the future, what you're likely to see, and probably on one chip, is you're going to see the CPU, GPU, and a bunch of heterogeneous specialized devices that serve maybe only a subset of the applications you run, but make those applications run a whole lot better. I mean, think about a small battery-powered device for watching movies. Wouldn't you rather run your video decode on a dedicated functional unit than use the CPU, particularly if it means you can double or triple the battery life watching movies? I think most people would agree that's a good use of the transistors on the chip. And I think there are lots of opportunities like that in the future. But this has really interesting, profound implications for people like me who have thought of themselves as software people. When we start co-designing hardware and software together, where's the boundary line? Where do software people and hardware people get together and talk about this division of labor between the two pieces? How do we talk about building something? For instance, you know, the example up there shows the Kinect, which is this fairly simple piece of hardware in that little device that connects to your Xbox. But really, it's a useless piece of hardware without a great deal of sophisticated software to process the fairly noisy information that comes back from the sensors on that device. So, you know, really, we have this really interesting world coming up where sort of hardware and software have to be co-designed, where you really need to sort of think about both of the pieces as an integral whole. You know, we've been in a great world for the past 30 years where basically there were PC manufacturers and then there were software companies, and there were standardized interfaces that allowed innovation separately on both parts. But as we increasingly integrate and specialize the hardware, that's no longer possible. The software people have to be involved in the discussions about where we're going. And let me just go through that. So let me shift gears and start looking at another trend, which is data. This is a great number. This is what the economists predicted, or this is what the economists claimed were the number of bytes of new information created last year, 2010. That's a tremendous number. That's the kind of number you used to see in chemistry discussions, where you saw Avogadro's number, 10 to the 23rd. Huge scale of data there, and anybody who's sort of in science has seen this many times in many different ways. And one of the interesting questions is, why all of a sudden do we have so much data? So look at these numbers. This was the cost of disk storage a decade ago. This is the cost of disk storage a year ago. As you can see, it's fallen many orders of magnitude. Disks obviously are a lot bigger, and it shouldn't be surprising to people. If you actually look at the trends, the capacity of a disk drive has been increasing 100% per year for, I think, about 15 years now, since the mid-90s. That's faster than Moore's Law, much faster than Moore's Law, and it's an exponential growth. So we have the disk capacity to be available, and like anything else, if it's available, people are going to fill it up. People are going to use it. I mean, you've all seen this in your own life. But, free storage is like free puppies. It comes with a lot of costs. People put a lot of information on the disk, and then they don't do anything with it. And this is sort of one of the real tragedies of data, is that, collecting information is a lot easier than using information. And it's even harder to use the information to make good choices. And I think that's where a lot of the challenges are going to come in the next few decades, is the processing of the data, not just the collection of the data. In the scientific world, you see this in ways that are very easy to document. People are running experiments that are collecting huge amounts of data in very short periods of time. People have been doing simulations and are continuing to do simulations that generate huge amounts of data and process huge amounts of data. We're archiving a large amount of the information that's available in the world. I mean, Google has this ambitious plan to literally put all of the books that are in print or available in libraries on the internet and make them available to people. And, consumer information. Clearly, every website that's out there is collecting a huge amount of information on the consumers that come to the website. And that information provides a lot of the value of these properties that are out there and the businesses that people are developing. Let me put some numbers to sort of back up these claims. So, in 2000, the Sloan Digital Sky Survey collected more data in its first week than was collected in the entire history of astronomy. You could say, well, this is the shift from analog to digital, but it really is a striking fact, and it's only gotten worse. So, the new telescope that's under construction in Chile will get 140 terabytes in 5 days, more than 10 years of the Sloan survey. The Hadron Collider at CERN collects 40 terabytes of data every second. That's 20 new disk drives every second just to contain the data that they're collecting. Just tremendous, mind-boggling amounts of data. And one of the real challenges, of course, is that put the data on a disk drive, you send it across a very, very thin straw, and getting it off the disk drive and actually doing something with it is a huge computational challenge. And you don't have to look to that part of science. There's actually another trend which is really striking as well, is genetics is becoming a mainstream consumer item. So the first genome sequencing cost roughly $3 billion for that sequencing. That number has been falling much, much faster than Moore's Law. So by the end of the year, it's going to be down to roughly $1,000 for sequencing a genome. So something that's available to medical practitioners and in fact, individuals at that price. Look at the amount of data that comes up when you start doing that. So a person roughly, genome can be represented in about 3 billion bytes of information. Multiply that times the number of people, we have 10K petabytes. But that's only the beginning, right? There are a lot of other living organisms on the planet that have DNA as well that's well worth sequencing. And so you can multiply that by many, many times and still not capture the huge amount of information that's out there that's potentially interesting to collect, analyze, compare, understand the differences, understand what they say in terms of the biological life of the entity that contains the DNA. So Jim Gray was obviously one of the real big proponents in sort of the shift from experimental to data-driven science. And the book that's there that was published by Microsoft Research, The Fourth Paradigm, is a tribute to Jim that collects together lots of papers by people who are in the forefront of data-driven science. And his observation, which I think should be quite clear to all of you, is that science has passed through phases. Originally, it was just experimental. You observed the world, or you did a simple experiment, and you made a claim about the future. In the past few hundred years, we've moved to a theoretical science where you use mathematics to describe and predict the future of the world. In the last few decades, we've been able to use computers and computational science to make simulations of things that are difficult to model mathematically. Jim's observation was that there's a fourth paradigm, which is data-driven science, where you collect huge amounts of data, observations about the world, and you analyze it using computers. So in some sense, it's a combination of the first three put together into something that's fundamentally different and new. And this science is really driven by huge amounts of data and computation in the cloud. So what's a cloud? You know, it's a buzzword. Obviously, everybody's heard it. You know, it's in the newspapers. You know, it's in Microsoft's advertisements. It's in everybody's advertisements. I come home and my kids say, "Don't you do that kind of cloud stuff?" So it's worth actually being a little bit more precise and sort of talking about the different types of clouds. And there are really sort of three broad categories, all of which are lumped under clouds. And it's worth distinguishing them, and then it's worth sort of saying, really, they're all sort of three manifestations of the same thing. So the first one is infrastructure as a cloud. And the purest example of that is obviously Amazon Web Services. You buy computing cycles on demand in the cloud, basically. You bring up whatever software you want on a virtual machine, and you have your computing resources, and there are some services around it, but really what you're buying is cycles. You know, it's an incredible convenience. You don't need the machine. You can use the machine when you want it. You can expand it. It's elastic. Second one is platform as a service, where there's software hosted that you build your software on top of. Windows Azure is a good example of this, where we're basically providing Windows of various sorts in the cloud. Office 365 is yet another example where we're providing Office and SharePoint as a starting point for building applications in the cloud. And then the third one is software as a service, where literally what you're getting is the service of the software, and you don't really bring up any sort of pieces yourself. And I think the clearest example of this is Salesforce.com, which has basically moved CRM into the cloud and taken it off of mainframes. All of these are cloud computing in the sense that the server sits there somewhere, it's run extremely efficiently, there's economies of scale, and it's available on demand as you need it. I think those are the key characteristics: efficiency and on-demand availability. And you know, there's a lot of excitement about this. Hopefully, you know, businesses look at this and they see lots of opportunities for cost optimization. And universities should be looking at this also and seeing lots of opportunities for cost optimization. You know, running a server in your lab with grad students may seem to be cheap, but if you look at the full costs, they're probably fairly large, both in terms of your students' time and also in the university's power and cooling and security issues. There are business efficiencies as well. You know, as a business, you don't need to hire people who know how to run machine rooms and build machine rooms. You can focus on core competencies. There are obviously issues about transfer of responsibility. You know, do you trust your cloud provider to provide an essential service to your business? And these are issues that are difficult but are being worked through. But you know, that plus this just-in-time provisioning, really sort of the ability to get resources when you need it, is an incredibly compelling story for a lot of the businesses out there, and also for a lot of other entrepreneurs. So let's take a little bit about the cloud. So the traditional view, you think of the cloud and you think of all these big, massive infrastructure pieces. And the answer is yes, these are big, massive infrastructure pieces. If you've ever visited a modern data center, the scale is just something that's totally foreign to people who do computers and computer science. I mean, you have an industrial plant basically run on the same way as a very, very large-scale manufacturing enterprise with a great deal of discipline. So Microsoft has been through this. We started off building data centers in a fairly conventional way, pretty much probably the way most of your data centers are running today, where you go and buy individual servers. This is a picture of a desktop server, but we used to buy them in the 1U pizza box and put them into the racks ourselves. This is a very inefficient way of building a computing capacity. If any of you have tried it, think about a data center with 20, 30,000 servers in there, and just imagine the packaging that you have to undo, the cardboard boxes that result from unpackaging 40,000 servers. And literally, when we did this, there were people whose job it was to recycle those boxes. Not scalable. So the second generation, we went to racks. We basically said, ship us a rack full of machines configured the way, and hopefully tested before you deliver it. So we literally just plug the rack into the power and the network, and it starts running. That wasn't enough. That was better, but it's still not. That's only a factor of 40 better. There are about 40 servers in a typical rack. We then went to containers. Containers contain about 2,000 servers, and we literally sort of roll them in on the back of a truck. These are standard 40-foot shipping containers. We plop them down. We connect power, cooling, and utility, and all 2,000 servers in there should light up. So that's another factor of 50 over the rack level deployment. Again, economies of scale, right? Basically, these things are really big. You should be able to get a lot more efficiency out of it. We're actually driving pretty hard and trying to change even this. This is not efficient enough. So the latest generation of data centers, which we're just starting to bring online now, we're asking the question, why do we even need a building if all the servers are in containers? And so the latest data center use these things called IT packs, which are these self-contained units that you literally roll in, put down on a concrete pad, connect the utilities to, and you don't really worry about what's around them. The ones that are in central Washington are under a roof, but there's no walls in there. And so in the middle of the winter, the snow comes blowing through the middle of it and sort of piles up around the containers. But it allows us to build a much, much cheaper facility. It allows us to spend a lot less time building the facility so we can meet demand by basically getting things online much earlier, much faster. And this is where the economies of scale come in, that companies like Microsoft and Google and Facebook and Yahoo and all these other companies that are out there in the cloud at very large capacity really have this opportunity to drive a lot of efficiency into the computing platform. Give you an idea. So this is the third generation. This is the one with containers. This is our Chicago data center, which came online about a year and a half ago. It cost us $500 million before we ever sort of put anything in there and started it running. So this is driving the desire to get rid of the building. And the numbers are obviously huge in terms of the resources that it required to build this data center. Give you an idea. The size of a data center is about 17 times the size of a football field. And this is actually a great unit of measure, by the way, football field. It's scale invariant. I can give the same talk in Europe and I can give the same talk in the United States because a European football pitch is about the same area as an American football field. And so in both cases, it takes about 17 of them to equal one of our data centers. But this just gives you a feel for the scale of what industrial practice is, the current state of the art. So, I've sort of shown you a bunch of pieces here, and you're probably wondering, so what does this mean? And the answer is, well, we now have enough computing capacity for us to do things that are different than what's happened before. And so what I'd like to do is now try to open your minds to sort of opportunities that are made possible by the combination of these low power, ubiquitously connected devices plus the cloud computing in the future. And the opportunity here is to make a big transition. So we've all sort of lived through this. We're now in the midst of this client plus cloud transition where you have things like your cell phone, your smartphone, and you have a cloud there. What's coming next? And so the argument that we're making and the argument that XCG is pursuing is that natural user interfaces, NUIs, are what is going to result from this. That we actually are going to try to use this vast amount of data, vast amount of computation, and different types of devices to make the user interface between computing and people much more like the interface between people and people, as opposed to what we've had for the last 50 years between people and computers. And we're going to do this by incorporating all the modalities that people use to communicate with each other: voice, expressions, and knowledge of the environment, gestures, multi-touch context. And you've already seen parts of this. You know, we have multi-touch interfaces. We have things like the Microsoft Kinect, where you actually can move your body and the computer can sense it and respond to it. And this is only the sort of beginning and the tip of the iceberg. You know, the vision that Craig Mundie, Microsoft CTO, was expressed a couple years ago, where he made the observation that he has a lot of assistants. A lot of people are working to make him a lot more effective in terms of doing his job and interacting with the world. But not everybody could afford a staff of people supporting them. And, you know, can we actually build computers, computing capacity that allows anybody to interact with their computer in the same way in which, you know, a person would interact with a staff of intelligent assistants? So, you know, instead of me having to sort of figure out all the details of a trip to a conference, I could literally tell the computer, I want to attend this conference. Please, you know, make sure that I'm there and registered to have a hotel room. Or maybe even not say that, it's just say, I would like to attend this conference, and have the computer figure out, you know, where the conference is, what the conference hotel is, arrange for the plane flights, book my tickets, book my hotel, register me for the conference. This is the kind of thing that comes up in my life all the time, and it would be great to not have to do the pieces and to sort of have an assistant for that. So let me pause at this moment and switch over to a video. So I think I'm, oops, they switched computers on me. So this is a video. Sorry, that didn't work. So as I was saying, this is a video from a marketing video from Microsoft talking about the cloud. It has a lot of very compelling visions of what cloud computing could be to people in a variety of different real-world contexts. It has a bunch of very cool-looking devices that the movie makers created to express their view of where we could go. And if you look at it, you see lots and lots of ideas about sort of this integration of computing devices into a very seamless whole in your life that makes your life work a whole lot better. Okay. Let me kill it. Okay, so if you look at the pieces of the video in more detail, what you see is lots of scenarios from the office, from work, where sort of the integration of the pieces becomes a lot more seamless. You know, for me, one of the sort of simplest and most compelling is that meeting where the woman picks up her slate and literally focuses it on the live board, and all of a sudden all the documents are there. Any of you who have ever sort of tried to share documents among a group of people would appreciate how much easier it would be if you could actually do that in the real world. And this notion of sort of seamlessness, that the computing is part of your world, and you don't actually interact with it with either, the old command line derivative interfaces or even the GUI interfaces, but you act with gestures that sort of correspond to the way you would normally do things. Where like a bunch of physical objects I could just reach out and pull to me, instead maybe a bunch of documents I could just reach out and pull to me. Or where, I walk into a space like the woman walked into the airport, and sort of I hold out this very cool credit card-like device, and it sort of tells me what I need to know. It doesn't put out a map of the airport, but it basically is sort of customized to the task at hand that I'm looking to meet somebody in the airport. Can we actually do things like this? And the answer is sure, we can do this. It's a huge amount of work in terms of figuring out how to build the pieces, how to integrate the pieces, how to figure out what the right user interfaces are. But it's a challenge for us in terms of computing. All of you know sort of that the sort of non-computer part of the world, the vast majority of the world, finds computers sort of non-intuitive, difficult to use, failure-prone, lots of bad things. They use them because they're useful, not because they like them. And that may distinguish them from the people in this room. But one of the challenges is to sort of get the computer out of the picture, basically provide the benefits of computing without the drawbacks. And I think one of the real compelling advantages of the new platform is it gives us a do-over. We basically can sort of say, look, we've tried to do computing this way. We've sort of exposed all the pieces to the people. It didn't work well. Let's try again. Let's try to build a user interface and an interaction paradigm that works for people. Obviously, any talk about the future and computing and so forth isn't complete unless we sort of talk about the problems. And I would argue that the biggest challenge to this whole vision is security and privacy. That, as we centralize and connect the pieces, the threats become larger because the pathways that allow us to sort of pull the pieces together and offer new experiences also allow other people to come in and disrupt the experiences. So, viruses were certainly a problem before the internet, but they spread much slower. Just like, disease spread a lot slower before we had jet airplanes. And privacy is the other part, the new part. As the information on us starts to be collected and aggregated, then there are new threats to us, threats that are much harder to put your thumb on than security. People have this very ambiguous view of what privacy is. For them, some people, telling some information to a website in return for the services of the website is okay. But then a slight shift in terms of what the website does with it, that they start targeting advertisements based on who your friends are or what your mail is. That starts to become uncomfortable for people, and everybody has a different limit. And so privacy is a very difficult and nebulous area, but one that's really going to come up again and again as we start to connect the pieces together, because the systems and the cloud are going to know a lot more about you and be able to make decisions based on that. So, and these are not, to make it even worse, these are not technical problems. If you look at it, security, privacy, these are legal issues, these are policy issues, these are things that society as a whole are going to need to discuss, come to some agreement, and then provide some mechanisms for actually enforcing. And to make it even more challenging, this is going to have to be worldwide, because no one country can literally sort of set the borders and set the standards that in a way that doesn't impact everybody else who's running services in other countries in the world. So these are real challenges to this vision of computing. So let me switch gears and spend the last couple minutes talking about the Extreme Computing Group, which is the group in Microsoft Research that Dennis and I are part of. We're really focused on this vision of client plus cloud computing with three different focal points. One of which is the improvements to the data center, basically the computing infrastructure. Can we make it cheaper? Can we make it more efficient? Can we make it easier to program? Another one is the client experience, and the third one is security and privacy. So our approach has been to sort of rethink this, basically to take the attitude that I expressed, which is this is a new platform, and it's not sufficient to just look at each piece individually and in isolation. Instead, we should be thinking about this combination ranging all the way from these data centers to the devices that you hold as a single holistic piece and ask, how do we make changes that make it more effective, more reliable, more secure, and look across the whole stack, both the software and the hardware stack. And we've been doing work in a number of these different areas to drive this vision forward. So one of the things we did is to rethink, what does it mean to build a server? So that black box, it's a little hard to see there, was our first server that we built. We literally took a bunch of Atom processor boards. Atom was Intel's low-power processor for the netbooks. And we put them in a rack, put them in there, and called them a server. And the reason it was interesting is that we actually then brought up Microsoft's data center software on top of these netbook processors and showed that it actually ran pretty well at fairly good power efficiencies. And this was one of those things that sort of like people started to say, wow. And you can actually now buy servers from a number of companies which are based on Atom chips. And for certain applications, they're actually a wise choice, but where you have scale-out capacity and you don't need a huge amount of computation for each task. Another thing we've done is work with Intel on their cloud computing chip. Basically, it was a 48-core chip with 48 low-performance cores, but a very, very high-speed network. What Intel viewed it as basically a slice of the data center put on a chip. We brought up Windows on it and looked at a bunch of studies to sort of understand its performance and understand the programming model, which was a non-shared memory model on this chip. Interesting experiment to sort of see the way the world could be going in terms of the building blocks for a data center. We've also been thinking about storage, asking the question of what comes after disks and flash, which is probably not the right way to phrase the question because disks aren't going away. They're just going to be augmented by other forms of persistent storage. Disks are still going to be necessary for capacity, but right now we're seeing flash becoming cost effective. Probably many of you have it in your laptops. In the next couple of years, it's going to come into the data center, and it literally does change the software stack. And there's an order of magnitude more performance out of a flash drive than a disk drive in terms of latency. And so you start asking questions about what that means to the software stack, both the operating system and the applications on top of it. And beyond that, there are even more interesting technologies like phase change memory, where literally we can integrate persistent memory back into the main memory hierarchy and get another order of magnitude of performance there. So the memory hierarchy is going to change, and this is all for the better. One interesting fact is that the least reliable components in your data center are the disks and the fans. And those are the mechanical components with moving parts. They fail the most often. So it'd be good to get rid of them. Another area where we've been very much involved is data center networking. We were a major player in a Microsoft research system called VL2, which basically rethought what it means to build the data center network. This is a typical picture of a data center network. So you have racks, which go to top of rack switches, which go to level 2 switches, and then go to aggregator switches. Every step up, you basically are oversubscribed by a factor of 10 or 20 to 1. So the amount of bandwidth available falls as you go higher up in the tree, and the cost goes up. Each one of those switches, as you go higher in the tree, becomes an order of magnitude more expensive as well. And there are a lot of problems with this. Basically, the communication bandwidth between any two machines in the data center are very dependent on where those machines are located. If they're in the same rack, you actually have pretty good bandwidth. You probably have a gigabit per second between those two machines. If they're in their two racks next to each other sharing a switch on the row, then the bandwidth is not as good, but it's not bad. If they're far away in the data center, then it's probably bad. This has a lot of implications in terms of how you write software. You have to think about locality within the data center, and it limits the size of the units of locality to racks. It also makes it very difficult for us to do things like migrating jobs between machines so that we can power down servers, because migrating a job between this rack and that rack may have large implications for its performance. So it has implications for efficiency as well as software development. And the VL2 network that we built basically gives you a uniform bandwidth between any pair of machines in the data center. And it also reduces the cost of the hardware infrastructure as well. Another issue we've been rethinking is how do you connect the wide area network into the data center? One of the issues here is that we would like to be able to geo-distribute computation. We'd like to be able to run between data centers, not just within a data center, both to get flexibility and to get failure tolerance. And the issue here is that you have tremendous bandwidth on the fiber, but coming into the data center, it has to get distributed to the individual nodes. And so the connection right now is fairly abrupt and fairly low bandwidth, and we need to find better ways of doing this. We've been working a lot on this issue of packaging and cooling. You saw the IT pack. This is a very interesting chart. Basically, this is a chart of temperature, humidity, versus where you're supposed to operate your computer. The very small red shape is where most data centers operated until recently. You know, if you walked into a data center, it was typically cold, 65 degrees, you know, and dehumidified. And you might have wondered why. And the answer is there was no really good reason except tradition. You know, if you looked at the ASHRAE, the Society of Refrigeration Engineers, they actually suggested that blue box there for running electrical equipment in the data center. And if you looked at that yellow box, it's actually what the manufacturers suggested. So if you read the data sheet for the server, you could have much wider range of temperature and humidity. Why does this matter? Well, it costs a lot to air condition a data center. If you can raise the temperature, you don't have to air condition as much. Even better, if you could just use outside air instead of air-conditioned air, you can get rid of the air conditioning equipment entirely and run your data center at a much higher level of efficiency because you don't waste the power to do things that you don't need to do to keep the machines colder than they need to be. We actually opened a data center in Ireland that does this. It literally runs off of ambient air. There is no air conditioning equipment in there. You know, you say it's easy in Ireland. So one of the real challenges, one of the things we've been looking at is, could we do this elsewhere? You know, could we run servers with ambient air at 50 degrees C, 120 degrees Fahrenheit? You know, there's literally there's no inherent reason. It's just that people haven't done this before. And then you also have to ask yourself, can we run this at 0 degrees C? You know, when the snow is blowing around the IT packs and we're sort of getting the air in there. That turns out to be easier because you can recirculate the heat from the servers to heat up the incoming air. It's the high temperature one that's actually a challenge because it raises issues in terms of reliability and power consumption. These are experiments that we've been conducting. And one of the other issues we're really interested in is this issue of reliability. Can we build systems that aren't meant to be serviced? You know, data center equipment has a fairly short lifetime, typically 3 years for servers at Microsoft, and then we just literally roll out the container or the rack, replace it with the new stuff, which is faster and more power efficient. Could we build a container that isn't meant to be serviced? It's sealed when you get it. Pieces of it fail over the 3-year lifetime. There's enough of it running at the end of 3 years that when you roll it out, it still has some value. There are a lot of advantages to this. We could pack the servers more densely. We could eliminate the errors and the failures that are caused by people servicing things, and that's actually significant. We could perhaps reduce the cost of the servers and the packaging by not making them serviceable. And so we're looking at these trade-offs as well. We've also been looking at sort of what happens if you start powering your data center off of irregular sources of energy, things like solar and wind energy, which vary in magnitude over time. You know, then the number of machines that you can power in your data center may vary over time. We've been very interested in sort of economic models that would get people to sort of adjust their computation to take advantages of the trends in terms of energy availability. And we built a small data center prototype which is powered entirely by solar and wind to allow us to do some experiments on this idea. And beyond that, sort of shifting into the software rather than the hardware realm, we've been really rethinking this issue of security and the data center. How do we build more secure data centers, or how do we build secure data centers? What are the hardware and software pieces, as well as the policy implications, policy changes that have to occur for us to be able to do this? My personal part is a part called Orleans, which is a programming model. One very, very pressing question is, if we're moving to this world of cloud computing, how are people going to develop software in it? You know, most people are not experts in distributed systems. It's actually a fairly subtle and tricky set of skills you need to build a reliable, scalable, distributed system. The idea behind Orleans is that we can take these concepts, take best practices from building these systems, build a programming model on top of it, and then give it to developers, and we make some simplifications to it which costs something in terms of performance, but provide a much easier way of building a scalable, reliable system on top of a data center platform. So, I've got about a minute, and this is my last slide. Basically, the vision in this talk that I outlined is client plus cloud computing, the availability of vast resources in the cloud plus lots more interesting clients allows us to build new experiences, basically change the way in which most people interact with computing and change it for the better, basically allow us to provide new functionality, provide much more seamless, powerful interfaces to the computing capacity. And to do this, we need to go and rethink many, many levels of the system hierarchy. We need to start thinking about how do we build even more cost-effective, powerful data centers than what we've built and the equipment in there. How do we program these data centers? What does the client software look like? How does the client interact with the data center? How do we provide security and privacy across this whole distributed software hardware stack? And then we can start asking the really truly interesting questions are, what are the user interfaces? What are the modalities? What are the killer apps that we're going to build on top of this? So thank you very much. And I think I have some time for questions. Well, then you shouldn't have.
So we have people with two mics. And so one of the things that I'm curious about is, as Jim mentioned, we've thought and we think a lot about the issues of security and privacy in the cloud. And I'm curious to get people's reaction from the research community, from you guys, how much thinking is going on in the academic research community on this topic. I would welcome an opinion.
Hello? Okay. This is Phil Young from George Mason. I have a question regarding the infrastructure side. You talked a lot of challenges we're facing to build the cloud computing and satisfy the computing for the end users. Let's say if we putting all those islands for computing or centralized computing facilities, and we have massive concurrent users to access the computing facility. For the network part, you mentioned that we need high bandwidth. For the cloud computing infrastructure we have at Microsoft today, for example, do you have kind of user survey about their satisfaction about their bandwidth, or in a more broad sense about the cloud computing? Once we centralize this computing, is the network good enough to support that?
Well, I mean, that's a good question. And the answer isn't simple because the network isn't simple and it isn't one network. But one thing I would say is that communications networking is as important as computation in this world. The two sort of really big changes from my experience in moving into this domain are the centrality of power and the centrality of networks. And so, I talked about several of the pieces. I didn't talk about several of the other pieces. So inside the data center, networking is currently our biggest challenge. The networks are inadequate in terms of bandwidth. They're not particularly reliable in terms of reliability. A lot of the failures within the data center, once you get past the fans and the disk drives, are due to networking. And then, of course, anybody who has a smartphone is well aware that the wireless networks are currently inadequate both in terms of bandwidth and overuse capacity as well. And so we face challenges in terms of almost all forms of networking. When we sort of think about new user experiences, networking is really very central to it. You can't send a huge amount of information and you can't assume really low latency in lots of situations. And that forces you to change both your goals and the system architectures that you build on. And so, these are areas where there's need for lots of innovation in the next few years. And, as I said, networking isn't really just sort of one problem. It's a whole different set of problems when you look at the different scales at which it occurs.
There was a slide you skipped over. Could you put the slide up on smart homes?
Sure. Sorry, I was driven by a clock. Proves that I guess you can get anybody to do any time you want for a talk if you... There we go. Is that the one you want?
Right. I just wanted to leave it up for a couple
Oh, sure.
You could even say a few words about
I could even say a few words about it. So, this is actually a really, really interesting context for thinking about this client plus cloud computing. Let me give you an example, one of which that we've been talking about and haven't actually done very much on yet. So right now there are pure electric vehicles, things like the Volt and the Leaf that are coming out that need to be recharged, particularly the Leaf. Suppose everybody who comes home from Microsoft drives into their garage at 7 p.m. at night, plugs in their car, and says recharge it. I can tell you the electric grid in most parts of the world is not up to recharging the electric vehicles. They require a fairly large amount of energy over a short amount of time, and the grid was not designed for this kind of surge. How do we manage that? Think about the question of how we actually do this. We would like people to move to these cars. I think they offer a very nice value proposition in a lot of places. But if people find that they can't recharge their cars and the cars are not useful because when they get up in the morning and want to go to work, they haven't been recharged or they have blackouts or brownouts and they get blamed for it, that's not going to be a very attractive scenario. So one thing to think about is basically an integration of the charging system with people's lifestyle. So maybe I plug it in and the utility sort of realizes that it's half charged, and tomorrow I'm driving to Microsoft and half a charge is more than enough to get me to work and home again. How does the utility know what I'm doing? Do I really want to expose my calendar to the utility and have them know where I'm going and what my appointments are for the next day? Probably not. So you start thinking through scenarios like this and you realize this integration of the pieces is both enormously challenging but opens up all these opportunities for improving not only sort of people's lifestyle but societal efficiencies. So we're working on a project called Aura, where basically I would have an agent in the cloud that would sort of own my schedule and would interact with the utility to basically sort of come to some agreement on my behalf about whether my car is going to be recharged, whether it needs to be recharged the next day. It would not disclose my information that I didn't want to disclose to outside parties. And this is only possible if the pieces are connected together, and they're only going to be connected together if there's something like the cloud, which has more than adequate data and computation resources that put them together. So that addressed the question, I hope.
Hi, it seems like some people find that building small servers using GPUs instead of CPUs, they find that they have a lot better price to flops ratio. Like, what do you think about building a larger scale data center using GPUs?
I think for certain types of applications, it makes a lot of sense. So if you have to do a lot of floating point computations and they can be put into a SIMD style, then the GPU is a lot better way of doing those computations than the CPUs are. And there's no reason why you shouldn't build servers around that. It goes back to the sort of point that I was making at the beginning. What's the maximum utility of a transistor on a chip? Well, if it's sort of used in a computing structure that solves your problem efficiently, then it's a lot more valuable to you. And so you'd want to build servers. And I think we're going to see this in not just GPUs, but we're going to see this in lots of different specialized functionality being added to machines in the data center. So, you'll look at the problem that you want to solve. You'll ask, is there a much more effective way of solving this problem using, fully custom or even semi-custom hardware? There are things called FPGAs, which are programmable logic, where you don't actually have to sort of fabricate the chips. You literally can sort of reprogram the chips to solve your problems. And for certain tasks, they can be incredibly effective at giving you large speed-ups and cost efficiencies. So yeah, I think the world's going to become a lot more interesting in the next couple of years in terms of what the computing platform looks like, both in the data center, and I think this is already true. If you look at your your smartphone or your pad, there's a lot of specialized hardware in there for power efficiency primarily, but it's great.
What do you think the biggest risks are for us not meeting this wonderful grand vision, Jim? It was a great talk. So.
A great question. So I already called out security and privacy, right? I mean, we may build this and people may be appalled at what we actually create and say, give me paper and pencil. I don't want to have anything to do with it. The other one is just literally that we find it too hard to build user interfaces that people can interact with. And I can tell you that's an area that Microsoft Research has been working on for as long as I've been here, which is almost 15 years now. And it's extremely difficult. Basically having a machine understand what's going on in terms of a person is very challenging. Give you an example. Eric Horvitz, who runs the machine learning group, built this really sort of compelling demo called the virtual assistant, where literally is sort of a server plus a camera, and he has this outside of his office, and it acts like an administrative assistant outside his office. And the camera's there, and you should walk up, and the assistant looks at Eric's schedule and sort of tells you something. Eric is at a meeting in another building. He's coming back. He'll be here in 5 minutes. So there's a great video of it on the Microsoft Research website. Look at it. But the video shows it working really well. So one time, Eric and I both walked up to his office when I had an appointment with him, and it didn't recognize Eric. This virtual assistant said, "Oh, 2 of you are showing up for the meeting. I only expected 1 person." So, as I said, there are huge challenges there, things that we literally don't know how to do. On the other hand, there are sort of huge opportunities for research. And I'll point out the Microsoft Kinect is an example like this, where sort of we built the hardware. The Xbox team built the initial prototypes, and they ran into some really hard problems in terms of taking the sensing information and turning them into models of where your body was moving and so you could actually sort of see what the person was doing. Microsoft Research jumped in. We built a system based on machine learning to sort of build a skeletal model, which works extremely well. All of you who've tried Kinect can sort of testify to that. Real opportunity to take a lot of ideas from the research community and apply them in new contexts that are incredibly compelling and exciting. So, as I said, there are a lot of reasons why this stuff might not occur, but I think the challenge is to make it happen rather than sort of think about why it shouldn't or couldn't.
Any comments on how we teach this in the university?
I should mention that Jim was a university professor at Wisconsin.
I was a professor, but we didn't have any of the stuff when I was a professor. That's a really good question, and not something that I've given a whole lot of thought to. I guess one way to think about it is, as Dennis said, I was a professor, and if I was a professor again, I would certainly be sort of trying to pull this stuff into my class, not only because I find it incredibly exciting and would hope the students find it exciting, but also because I think that this is what they really need to know. I would be teaching them about distributed systems. I would be teaching them about machine learning. I would be teaching them about networking. All the sort of building blocks of this, and I would be encouraging them to think about computing in terms of sort of interactions with people in these client plus cloud scenarios, not just the traditional, desktop or, batch processing scenarios that have dominated computers, or at least dominated when I was teaching it. So yeah, I think, if you just look in this world, I think you can find things that students are excited about that are relevant to them. And, my experience has always been that when people are excited about it, it's a lot easier to teach them. Back there.
I
Hi, this is Lukas Kensel from the Czech Technical University in Prague. I wanted to ask about some kind of the architecture perspective of the cloud. So far, what we've seen are mostly pictures where we see huge, large data centers on one side and then clients on the other. I've also seen propositions from people at conferences that argued for some intermediate, smaller cloud center, something like something called cloudlets that would perhaps stand in between the large cloud and the client, and offload some of the processing, be closer, deal with some of the latencies, and simply act as an intermediate steps. What is the position of Microsoft on this? Where do we stand?
So we already have that. They're not called cloudlets. They're called CDNs, Content Distribution Networks. Akamai being the major one, Microsoft has its own as well. And the idea here is that if you centralize everything in a few large data centers, there are two problems, one of which is just literally latency. It takes tens of milliseconds to transmit information from one side of this country to the other, let alone around the world. And that latency starts to become very significant if you have a few hops back and forth for an interaction. People start to perceive it. The second one is literally just the cost of moving all this information across the same set of pipes when you could cache it much closer. And so the original idea behind the content distribution networks were that you cached web pages in servers in ISPs. So literally sort of closer to the users, you had a cache of the web pages. That's evolved, and it's no longer just static content that's cached there. Literally, you can put arbitrary computation on these servers within the ISPs. And in some sense, it's sort of pushing parts of the computation out of the data center into these subsidiary data centers that are closer to the users. And I think it's incredibly important because a lot of these scenarios are very much driven by interactions with people which are latency limited. So I think you're going to see that. On the other hand, other people sort of say, why do we even need data centers? Let's push everything out. And that doesn't work either, right? There are certain scenarios where really centralizing a lot of resources together and storage and high-speed networking capability allows you to do things that are different. The canonical example in my mind is search. The Google search engine or the Bing search engine. It's literally tens of thousands of machines in a data center. And the reason that they're in a data center is that they need to communicate and that there's a great deal of utility at sort of having it as a centralized resource that can be shared among many searches, as opposed to trying to physically push it out. So I think you're going to see a mixture of both. I don't think you're going to see only large data centers, and you're certainly not going to see just sort of small distributed data centers. You need a combination of both. So, Dennis.
Great. We're out of time now, so let's thank Jim one more time.